Hello everyone, welcome back to the YouTube channel of Canara Engineering College. In today's video session, we'll be discussing regarding analog counters. So this particular topic comes under module 5 of analog and digital electronics. So up till now, in this particular topic, we have discussed regarding registers and register transfers. We have also checked regarding the various types of registers, how basically a register will be transferring a data from one register to other register, how is it facilitated, and lot other things regarding registers has already been discussed. We have also discussed regarding what are the basic building blocks that are used in order to build the registers, and also we have checked regarding the various ways in which the data can be loaded and it can be removed from the registers. In today's session, we'll be looking regarding counters. So what basically are these counters? So as it was discussed, counters are the devices which will be keeping the count of the sequence that occurs. For example, you can consider the speedometer of the bike. So as an example, what we can do here is you can consider the speedometer of the bike. So what does the speedometer of the bike do? The speedometer of the bike normally will be keeping the count of the distance what has been covered. So what we can say is initial count in the speedometer of the bike. Let us say it is something like this. So initially it will be 0, 0, 0 and 0. After a particular distance, it becomes 0, 0, 0, 0, 1. And this goes on up till something like 0, 0, 0, 9. After 9, it will be becoming 0, 0, 0, 1, 0. And this goes on as such. So finally, it will become 0, 0, 0, 2, 0, and this goes on, isn't it? So this is how normally the speedometer of the bike will be counting the distance what has been traveled by the vehicle or by your bike. So basically counters are the ones which keep count of the sequence that occurs. The sequence what is happening in the speedometer of the bike is the rotations that is being made by the wheel of the bike. Based on the rotations that is made by the wheel of the bike, there will be counts that will be recorded in the speedometer of the bike. And the count what is happening here is always in the upward fashion. So this will be going in the 0, 1, 2, 3, 4, 9, after that 10, 11, 12, 13, 14, 20, and this goes on. So basically this is how a counter will be functioning. So we'll check what are counters. We'll check what are counters. So as it is said, it is a device which will keep the count of sequences that occur, and the sequences what occurs will be fed to the counter as pulses. So based on the pulses that are being fed to the counter, these pulses are recorded. These pulses are recorded by the counter, and the recordings what has been done by the counter will be displayed in the counter as counts. So this is what it does, isn't it? So normally if you consider the speedometer of the bike, so speedometer of the bike will be recording the number of rotations that is made by the wheel of the bike. So normally that will be sent to the speedometer as pulses. So for every pulse that is being sent to the speedometer count will be incremented by 1, and that is recorded, and that record can be seen by you as the distance that is being covered by the bike. These counters are broadly categorized into two categories. One of the counter is called as asynchronous counter, and the other one is called as synchronous counter. One is asynchronous and the other one is synchronous one. So how basically this classification goes on as asynchronous and synchronous. So let's get back to this device. Let's get back to this device in order to have a better look into this. If you look into this particular counter, you can see these are all the devices which has stored some data, isn't it? So what I can tell you is This is basically, if I consider this particular device, what it is present here, I can call it as a 5-bit register. And internally to the register, I can say this registers are made up of flip-flops. So basically, this is what I have been studying all this particular days. So counters are also registers, but this registers has got the capacity to count the sequence based on the pulses that is received by this particular register. So when I say it's a register, it's made up of flip-flop. So when I say it's a flip-flop, it is quite obvious that this flip-flop needs clock inputs. This flip-flop needs clock inputs. This clock inputs are nothing but the pulses what has been generated by the sequences. So normally when a sequence occurs, that sequences will be nothing but pulses. These pulses are converted into clock inputs, and these clock inputs are fed as input to the registers. Based on the clock inputs that has been fed to the registers, these registers will keep on incrementing or decrementing the count as it has been designed. So based on the clock inputs what is being fed to the registers which is used to design a counter, I categorize my counters into asynchronous and synchronous counters. For example, let us say this is the counter. For example, let us say this is your counter. A 3-bit register has been designed to a counter. So when I say it's a 3-bit register, it is made up of 3 flip-flops, isn't it? It is made up of 3 flip-flops. And all these 3 flip-flops will be needing clock inputs. The way in which the clock input has been connected to this particular flip-flops, which in turn makes up a counter, will be helping me categorize my counters into asynchronous and synchronous. So let me open it up. This is one flip-flop. This is your second flip-flop. And this is your third flip-flop. If the clock input is given only to the first flip-flop, and if the output of the first flip-flop serves as a clock input to the second flip-flop, and if the clock input of the second one serves as a clock input to the third flip-flop, which in turn makes up a counter, these kinds of registers are called as asynchronous registers. Asynchronous registers means the flip-flop, or asynchronous counters means the flip-flop which makes up a counter will be fed with only one clock input. The output of the second or consecutive stages will be acting as clock input to the upcoming stages. When I speak about synchronous counter, let us say these are the flip-flops which makes up a synchronous counter. So these are the flip-flops which will be keeping the count. So the clock input what will be connected to the flip-flop will be connected in this fashion, which means that clock input will be individually connected to each and every flip-flops, which in turn makes up a counter. So this is your synchronous counter and this is your asynchronous counter. Both the counters will be giving you the count of the sequences that occurs with respect to the pulses that are being fed to the counter. But when it comes to the speed, normally my synchronous counters are faster when compared to the asynchronous counter. This I can compare, or comparatively I can say this is slower when compared to the synchronous counter. Quite obvious. The reason why this will be slower is the clock inputs will not be fed at a time to all the 3 flip-flops, isn't it? Initially this flip-flop has to work. Only after this flip-flop can produce output, my second flip-flop can receive the clock input. After the second flip-flop produces the output, my third flip-flop can produce the count. Whereas here, all the 3 flip-flops will be working together, because of which this will be comparatively faster when compared to the asynchronous ones. Other than this particular classification, what we have done here, we have other classification in which we categorize it into up counter and down counter. We call it as up counter and down counter. So let's check out what is this up counter and down counter basically are. Up counters are the counters which will be counting from 0 to 9 or higher digits in the upward fashion or in the increasing fashion. That is what is your up counter. Down counters are the ones which will be counting from higher number to the lower number or from the higher sequences to the lower sequences. Normally the counters what I use in my day-to-day life are 90% of the times up counters. Only for some essential or necessary applications we'll be going with the down counter. So this is the basic introduction to the counters. So I have told you what are counters, what is it made up of, how does it basically function, how does it actually count the sequences, what are the general classifications or categorizations of the counters, and we have also checked which one is the fastest and which one is the slowest. You can call this asynchronous counters as ripple counters. You can call it as ripple counters also. You can go with the word ripple counters. Other than this, we have broad category of classifications for the counters, something like you can call it as decade counter, you can call it as universal counter, you can call it as up-down counter, you can call the counters by the name based on the flip-flops, what you use to design them. For example, if I say I have a 3-bit counter here, I say this is a register, these registers are in turn made up of flip-flops. These flip-flops can be made up using D flip-flop, T flip-flop, SR flip-flop or JK flip-flop also. So you have vast variety of classifications out of which this asynchronous synchronous up counter and down counter are the major ones. Moving on further, we'll directly get into the design of binary counters. So as we are dealing with digital electronics, whatever count a counter is going to give, it should always be in a digital fashion. You cannot say, sir, I want a counter which will be counting 0, 1, 2, 3, 4, or you cannot say 9, 10. It cannot, your counter, what you are intended to study, cannot give you the numbers in this fashion because we are studying digital electronics and I want my count also to be coming in the binary fashion. I cannot give you a decimal count. Yes, the count what comes out of this particular counter can be converted into decimal, or you can connect it to a decimal converter and you can see the count. But what we are restricted as, we need to restrict ourselves to the binary counters. That is what the title says here, design of binary counters. So let us take one example with respect to asynchronous counters, or you can call it as ripple counters also. Even though this particular topic is excluded from your syllabus, we'll just have a look into this asynchronous counters, how this basically works. So what you can see here is, this is the design of the counter. The thing what I forgot to tell you is, when you are taking the flip-flops, I told you they are nothing but flip-flops, right? I said that these flip-flops will be combined together in order to make up a counter. Now the question what obviously rises to your mind is, sir, how do I select the number of flip-flops to design a counter, For example, let us say that you need to be having a counter which will be counting till 8, okay? I want a counter which will be counting from 0 to 8. So it will be 0, 1, 2, 3, 4, 5, 6, 7, 8 is what the count should go on. But how many counts it is? Check out. 1, 2, 3, 4, 5, 6, 7, 8 and 9. So totally you need to be designing a counter which will be giving you 9 counts, isn't it? You need to be designing a counter which will be giving you 9 counts. So normally the counts of a counter is defined by the word mod. So as it is 9 counts here, I say I need to be having a counter, or I need to design a counter with a mod 9. This mod 9 means number of counts that counter is going to give you, or that counter is going to count. For example, if you say it's mod 10 counter, you need to ultimately understand that this counter is going to give me 10 counts. It might start from 0 to 9 or it might start from 1 to 10. That is of no issues with respect to me. That depends on the design. But whenever you come across the word mod 10 counter, mod 5 counter, mod 6 counter, you need to understand that mod refers to the count what the counter is going to count. So let us say I need to design or I need to rig up a circuit which will be giving me 9 counts. So 9 counts means normally if it is a digital counter or if it is a binary counter, it goes like this. This is my first count, second count, this will be your third count, and the last count will be 1, 1, 1. This will be your last count. So normally the counts what has to be counted by the counter will be decided by the flip-flops, or how many flip-flops are you going to take based on the mod. So normally that goes like this. So if you want your counter to be counting from 0 to 8, let's check out 2 to the power, how much is 8? So 2 to the power 3 will be 8, isn't it? 2 to the power 3 will be 8, which means that if you need to have a counter which will be counting from 0 to 8, you need to be taking 3 counters, or you need to be taking, you need to be taking 3 flip-flops. You need to be taking 3 flip-flops. That is what it says here. So this may be the maximum count what I am showing here, but number of flip-flops is decided by the maximum count what you are expecting your counter to count. For example, if it is mod 4 counter, or you say it's a mod 3 counter, sir, I need to be having mod 3 counter. Mod 3 means 0 to 0, 1 and 2, right? 0, 1 and 2. For this, I need to take 2 flip-flops. For example, if it is mod 5, for example, if it is mod 5 means it has to give you 5 counts. So 2 to the power 2 is 4, which means that 2 flip-flops can be giving you 4 counts. So you need to be taking 3 flip-flops. There are a lot of things to be studied here. There are a lot of things to be studied here. You might say, sir, if I take 3 flip-flops, is it not that it will be giving me 8 counts? It will give you 8 counts, out of which I need to reduce the 3 counts, which we'll study later. So ultimate thing what you need to understand here is, if you are designing a counter using a flip-flop, the number of flip-flops depends on the number of counts what your counter is going to count. Moving on further. So as I said you, this is not included in the syllabus, but still let us have a look into this. So it's an asynchronous counter. So you need a counter, please concentrate here. You need to design a counter which will be counting from 0 to 7. So how many counts total? See, again it got back to 0. So how many counts in total? You need to be designing a counter which will be counting 8 counts, right? You need to be having a counter which will be counting 8 counts, or you need to say I need to design a mod 8 counter. When you say it's a mod 8 counter, how many flip-flops are you going to take? You will be checking what is 2 to the power 3. 2 to the power 3, 2 to the power how much is 8? 2 to the power 3 is 8. So you have taken 3 flip-flops. See here, 1, 2 and 3 flip-flops. Sir, how the connections and all are done, we'll check it up later. Don't worry about the connections because we need to design them individually. So, first clock gives you first count, which means that without giving any clock input, see how designed it. See, the clock input is given. Clock input is given. You can check the clock input is given only to the first flip-flop, not to the second one. The clock input to the second one will be the output of the first flip-flop. The clock input to the third one will be the output of the second flip-flop, isn't it? Which means that this is clearly an asynchronous counter. I told you asynchronous counters are those counters in which my clock input will not be given to all the flip-flops. So that is what it is done here. These are all your outputs. The output of the first flip-flop is tapped out, the output of the second flip-flop is tapped out, and output of the third flip-flop is tapped out, right? And the data J and K are all connected. J and K are all connected to VCC. This is just for the example. As an example, we have just connected it to VCC. There may be some other connections what we need to study when we actually look into the design part. So when no clock input is given, this will all be set to 0, 0, 0. So 0, 0, 0 automatically means it's the first count. When you give the first clock input, see here, when you give the first clock input, When you give the first clock input A, it's a negative edge triggered. When you give the first clock input, your counter or your registers or your flip-flops, which in turn makes up the counter, will show 0, 0, 1. So it will show 0, 0, 1, which means it is equivalent to 2, right? After that, when you give the next clock pulse, it will show the count 0, 1, 0. That is, this will become 0, 1, 0, which means it is equal to 2. When you give the third clock pulse, it will become 3. When you give the fourth one, it will become 4. When you give the fifth one, it will become 5. When you give the sixth one, it will become 6. When you give the seventh one, it will become 7. When you give one more clock pulse, see here. You can see one more clock pulse here. When you give one more clock pulse, you can see it is again set back to 0, which means that the counter what you have designed here is a mod 8 counter which can count from 0 to 7. 0 to 7 will be 8 counts. Design part we'll study later. Don't worry, sir. How did you connect J and K to VCC and all J and K are connected to VCC? Is it the same for all the registers? No, it is not the same for all the registers. The design part varies. We'll study about the design later. But right now, I just wanted to give you an idea regarding how the count will go in an upward fashion when the clock inputs are given. See, no clock input, no count, which I can consider to be the first count. Second clock input, it has become 0, 0, 1. Second count, third count, fourth one, fifth one, sixth one, seventh one, eighth one. After the eighth count, it will not go to ninth count because the maximum things are done. So it has to reset back to 0. That is what it happens in your vehicles also. After the if you have seen our analog speedometer of the bike, maximum it can go up to 1 lakh. After 1 lakh, it will all reset back to 0. It will all reset back to 0 and it will start counting again. The same thing. And the count what is happening here, this is going in the upward fashion, right? So you can call it as asynchronous up counter because it's counting in the upward fashion. And this is a timing diagram. This is a sample circuit diagram, not the exact circuit diagram. Circuit diagram we'll check out later. Normally in case of your counters, which you have designed using flip-flops, the complemented or inverted output is not considered. It is not considered until and unless my design part demands it. My design part says that I want that output, which we will study in the upcoming sessions.